Okay, the Chernoff bound, well, this event is bounded by e to the power minus s times a is here, times the expected value of e to the power s times x. Again, I will make use of the characteristic function. If you remember, the expected value of e to the power sx is equal to the characteristic function evaluated at omega equals minus j times s. Okay, so I do that here. This is the characteristic function of the exponential distribution. If you just look at the notes from last week, therefore just plug in minus js instead of omega, you get this expression, e to the power minus sa lambda divided by lambda minus s. To minimize this, to optimize the Chernoff bound, I differentiate this expression with respect to s, which then I equate to 0 and solve for s, and then I get s equals lambda minus 1 over a. So this is the value of s that makes my Chernoff bound this the tightest. But remember again, let me uh, uh, again remind you that this should be greater than or equal to 0, because that is the condition for which the Chernoff bound is valid. Okay, so therefore the Chernoff bound will be useful only when lambda minus 1 over a is greater than or equal to a. So lambda is greater than or equal to 1 over a, or in other words, a greater than or equal to 1 over lambda, which is the mean. Okay, so this Chernoff bound will be valid to the right of the mean. This is important. Okay, you have to be aware of where the Chernoff bound works and where it doesn't. So just plug in this value for this quantity, x exceeding k over lambda as in here. Now, we obviously know this quantity from the complementary CDF of the exponential distribution. If you remember, well, the exponential distribution was probability x being less than or equal to a is 1 minus e to the power minus lambda a for a greater than or equal to 0. And if you take the complementary CDF, that is just e to the power minus lambda a. And instead of a, if you just put k over lambda, you get e to the power minus k. So that is the exact value, theoretical value, which we know. But let's just see how the Chernoff bound behaves. So just to this value here, well, of course, instead of a, just put k over lambda, this value here. And instead of s, put lambda minus 1 over a, and which a is k over lambda. Arrange it, you get k times e to the power minus k plus 1. Okay, so I've got k. So the k component increases as we go further away from the mean. But at the same time, I have a decaying exponential, okay, which goes to 0 much faster than k. And for that matter, it also goes to 0 much faster than both this and this. So beyond the point for which this and this are equal, which actually in this example happens when k takes the value of 0.0, 6.0 to something, beyond this k value, Chernoff bound is better than Chebyshev. And it's much better because it decays exponentially. So the bound gets tighter and tighter compared to Chebyshev inequality. Okay, this is the exact value, and this is the Chebyshev, the Chernoff bound. Now, as I said, these bounds are useful when you do not know the distribution. So you might ask, we have worked on the Chernoff bounds for the Gaussian and the exponential distribution for which we know the distributions. The answer to that would be one, I just wanted you to see the behavior of the Chernoff bound, and number two, sometimes you do not know the distribution, but you might know the characteristic function or some sort of a generating function, because it might be a transformation or let's say a sum of other random variables. and you may not need to actually um, take the inverse transform to obtain the actual distribution, but you can work with characteristic functions to put an upper bound on the probability. Okay, so we will talk about how the characteristic and generative functions are useful when we talk about functions of random variables or transformations of random variables. So when you have the characteristic function, you can actually, instead of back transforming it into the distribution, you can work with the characteristic function to produce an upper bound of any probability.